In this section, we'll look at standing sound waves. A sound wave that is confined, such as in a pipe or an air column, can also produce standing waves at certain frequencies. Note that a sound wave can reflect off a closed end of a pipe, but it can also reflect off an open end. So we have three different cases. Air columns that are open at both ends, such as the flute, or closed at one end. An example of this is a clarinet. Or an air column that's closed at both ends. This could just be a pipe that's closed at both ends, or it really could be any chamber, even a garage or a shower stall. For now, let's consider a pipe that's closed at both ends. At each end, the air is pressed against the wall or against the end of the pipe, and there can be no displacement at that point. So that means each closed end of the air column must be a displacement node. So I've drawn in here displacement versus time for this air column, so we have to have nodes at both ends. Now there will be many different harmonic patterns. I've chosen to draw the second harmonic here. And remember that this is also a pressure wave. A sound wave is a variation of pressure. And the pressure function is also sinusoidal, and it's shifted by 1/4 wavelength from the displacement. So if I shift this second harmonic by 1/4 wavelength, we end up with a pressure antinode at the closed end. And this is really the change in pressure from atmospheric pressure. So we see the greatest change, or the pressure antinodes, at both closed ends. We can also notice that the pressure function is exactly inverted with respect to the displacement function. So where we had a displacement node, now we have a pressure antinode. And where we had a displacement antinode, now we have a pressure node. Okay, so I've drawn now or adjusted my previous drawing to show you what happens when one end is open. At that opened end, the pressure there has to match atmospheric pressure. So that means that we need a pressure node. And since the displacement function is shifted 1/4 from that, we must have a displacement antinode there. So we'll get into the specific resonances that we see for this open-closed pipe, but for now, what's important to know is that we have a displacement node at a closed end and a displacement antinode at an opened end, and then they're reversed if we're looking at the pressure function. Example 3, a directional loudspeaker is a device that is able to focus sound into a narrow beam. The beam is aimed at a wall, and interference between incident and reflective waves of wavelength lambda results in constructive and destructive interference. At what distances from the wall could you stand and hear no sound at all? Express your answer in terms of the wavelength. Okay, so first of all, we hear sound by variations in pressure at our ears. So you won't hear a sound if your ear is at a pressure node, which means there's no variation from the atmospheric pressure. A pressure node is a displacement antinode. So we're looking for when you hear no sound, which will be a pressure node, and a displacement antinode. Okay, and I've drawn here the speaker and then the wall. So these are the displacement nodes and antinodes. We know that the displacement at the wall is going to be a node, just like the end of an air column. So the node there's a node there. So we're interested in these antinodes. These are the positions where you'll hear no sound. So the distance to the first one is lambda over 4. This is because if we're looking at any standing wave, we went over this before, but the distance from between two nodes is half a wavelength. So the distance from a node to an antinode is 1/4 wavelength. And okay, so we have 1/4, and then the next one will be all the way to this antinode, which is 3/4. So 1, 2, 3. So that means that no sound will be heard. No sound at D equals lambda over 4, 3 lambda over 4, and we could keep going to get to any further antinodes. So 5 lambda over 4, 7 lambda over 4, and these are all distances from the wall. Okay, let's go through the three different types of air columns and their corresponding resonance patterns. To start, if we begin with the closed air column, we have the same boundary conditions as we saw for standing waves on a string. Because the air column has two closed ends, both ends have to be nodes, and that's what we imposed when we worked through the theory for standing waves on a string. So it would look very similar here. So the patterns look like this. If we look at displacement, we have two nodes on either end. So one antinode for n equals 1. N equals 2, we have two antinodes. And n equals 3, three antinodes, just like we saw before. And we could keep going, n equals 4 and 5. And so if we want to draw the pressure functions, we can just look at the displacement function and invert that in a sense. So where there's a displacement antinode, we need to draw a pressure node. So for n equals 1, we need pressure antinodes at both closed ends, and then we need a node in the middle where we have a displacement antinode. So it looks like this. Then n equals 2, we have two antinodes, so we'll need two nodes, and again, both ends need to be pressure antinodes. And then similarly for n equals 3, where we had three antinodes, we now have three nodes within that air column. So I would suggest remembering how to draw the displacement patterns and then using that to draw the pressure patterns if needed. Okay, I've drawn this again for a closed pipe. So again, we have our displacement patterns here. And let's just look at them to count out the wavelengths. So still between a node and a node, that's half a wavelength. So here we have L equals lambda over 2. And then here we have two half wavelengths. So we get L equals 2 lambda over 2, or just the wavelength. And if we count here, we have three half wavelengths. Okay, so we have L equals 3 lambda over 2. And we can just rearrange that to see the pattern. So we get lambda n equals 2L over n if we rearrange this. And then we also have Fn equals nv over 2L if we just plug that into v equals lambda f. And we've done all of that before because this is exactly the same as we saw for the standing wave on a string pattern. So we end up with the same relationship, and n is 1, 2, 3, and 4. So the same equations here, and also the terminology is the same. So we have n equals 1 is the first harmonic or the fundamental frequency. N equals 2 is the second harmonic or the first overtone. And then n equals 3 is the third harmonic and the second overtone, and we could keep going. Okay, the diagrams look a little bit different for an open air column. So remembering that at both open ends, we need a displacement antinode. Then we're essentially filling in the simplest resonance pattern that could be produced at n equals 1 and increasing the number of nodes for each diagram from there. So n equals 1 has antinodes on both ends and one node in the middle. Then n equals 2 has two nodes with antinodes at both ends. And n equals 3, three nodes, and making sure that each end is an antinode. And then, of course, we can fill in pressure again, just again inverting the diagram. So where we had a node in the middle, we need an antinode in the middle for the pressure diagram. And here we had two nodes, so two pressure antinodes. And then here we have three nodes, so we get three pressure antinodes. And then, again, those open ends have to be at atmospheric pressure, so they're pressure nodes at those ends. All right, let's look again at the diagrams for the open air column and count the wavelengths. So if we look at n equals 1, our simplest pattern with one node in the middle and the antinodes at two ends, this is half of an antinode, or the distance from an antinode to a node, which is a quarter wavelength. And this is another quarter wavelength here, all the way to the end. That's the other quarter. So here we still get L equals lambda over 2. And then if we do it for the second diagram, we have a quarter wavelength, a half wavelength for this full antinode, and a quarter at the end again. So here I still have L equals lambda because we have a half plus 2/4 and we get the same relationship as we had before. Then over here, this is a quarter. We have 2/2. Those are wavelengths. And then we have a quarter here at the end. Okay, so and adding those up, we have one full wavelength, so L is lambda over 2 plus lambda over 2, plus 2/4, so we get L equals 3 lambda over 2. And you should see what I'm getting at here is that even though the diagrams look different, we have the same mathematical relationship between the resonance number and the frequency and the wavelength associated with that resonance pattern. So same equations as for a standing wave on a string and a standing wave in a closed air column is lambda equals 2L over N and F is NV over 2L. And again, it's a complete harmonic series. So N is a positive integer. And of course you can draw the pressure as I was showing, which are on this side. And again, we do have the same labeling. So N equals 1, first harmonic, fundamental, and then I won't go over them again, but it's all the same as before. Okay, the last case is the most interesting. So let's look at the open-closed air column. This is closed at one end and opened at the other. So at that closed end, we need to have a node. So we have that here. And then we need an antinode at the opened end. And we need, for the first resonance, we can just connect that in the simplest pattern, which looks like this. So there is one node in total. Now the next level or the next resonance, we can add a node. So we have two nodes and we still have that open end being an antinode and one more node for the next resonance pattern. I'm saying this because it's helpful to think of these in order of resonance when you're drawing the patterns, but actually these are labeled with odd integers. So we have n equals 1, 3, and 5. So the first harmonic, third harmonic, and the fifth harmonic. And only odd harmonics exist for the open-closed air column, and I'll show you why with the theory in a second. So now if we draw the pressure diagrams, when we invert this displacement diagram, it looks like it's actually just mirror reverse this time. So here we have a pressure node at the opened end as we need, and a pressure antinode where we had the displacement node. And then flipping this one, we have our pressure node at the opened end, and then pressure antinode, and then inverting this one, we end up again with the mirror reverse for n equals 5. And we could keep going. So let's look at that theory. Okay, I've left some room so we can look at the theory for the open at one end or closed at one end air columns, since they are a bit different. So let's look at counting the wavelengths. Here we have lambda over 4. So L equals lambda over 4, which is different than the previous 3 diagrams we've seen. This one is lambda over 2 plus a quarter wavelength. So for this one, we get L equals 3 lambda over 4. And here in the last diagram, we have a half, and then another half, and a quarter at the end here. So this is 5 lambda over 4, if you were to add those up. So you can see that we have a relationship of L equals n lambda over 4, as long as n is odd, 1, 3, and 5. And there's other ways to write this series, but this is the conventional way. L equals n lambda over 4, or lambda sub n equals 4L over n, and then F equals NV over 4L. And these two relationships, we have n is odd, 1, 3, 5, 7, 9, and we could continue. So this is actually called an odd harmonic series. So these are really the two important relationships for this open-closed pipe. And we get this frequency again just by plugging into the wave equation, V equals lambda F, and we plug in for lambda and then rearrange for f, and we end up with that. So I wanted to go over the labeling here since it's a little bit different since only the odd harmonics exist. And I've drawn the pressure functions down here. We can label these, of course, on the pressure or the displacement functions. So the pressure, again, is inverted, as I explained. So we'd call n equals 1 the fundamental frequency, or the first harmonic. N equals 3 the third harmonic, or the first overtone. So now n equals 3 is the first overtone. And then n equals 5 is the fifth harmonic frequency and the second overtone. And then, not to confuse you, but we could also talk about the order of resonance occur, and this would be the first occurring resonance, the second occurring resonance, and then the third occurring resonance. But generally, if you're describing it, you can stick to this terminology since that's the basis here. Just like standing waves on a string, these are resonant frequencies. So at these frequencies, the system is in resonance, and we'll hear the loudest sound. So that's the sound with the greatest amplitude. And in a string instrument like a guitar, when that string is plucked, the string will naturally play a sound at its fundamental frequency. However, with a wind instrument, if air was blown into an air column, almost all frequencies, or all audible frequencies, are played, but the resonant frequencies are amplified. The figure to the right shows the pressure standing wave pattern in an 80 centimeter long tube when the tube is filled with an unknown gas. If the frequency is 500 hertz, what is the speed of sound in the tube? Okay, so first of all, is it open, open, or closed, closed? We know for sure it's one of those. The boundaries at the end are the same. And since this is pressure and we have pressure nodes, then that must mean that those are both open ends. So this is open, open. Okay, and then we have the second harmonic, because we can see by this pattern that it's n equals 2. And we know L is 0.8. And then this must be F2, which is 500 hertz. And at the second harmonic, we have lambda equals 2L over n. So 2L over 2. So let's just write lambda equals L. Okay. So lambda equals L, so then V is going to be lambda F, which is LF. So 0.8 meters times 500 hertz gives 400 meters per second for the speed of sound in the tube. Example 5, with a particular fingering, a flute plays a note with a frequency of 880 hertz at 20 degrees Celsius. The flute is open at both ends. A, find the air column length, and B, find the frequency it produces when the temperature is -5 degrees. Okay, so since this is an instrument, we can assume that it's naturally playing at its fundamental frequency, which is 880 hertz, or at least that's the frequency of sound that's amplified. And then we know that the speed is 343 meters per second. You could calculate it using the formula for the speed of sound in air, but that was one that we can remember as well at 20 degrees. And then we can find the wavelength, which is V over F from the wave speed equation, so 343 meters per second over 880 hertz, so 0.390 meters. And then we know that lambda equals 2L over n. So 2L if it's lambda 1. So L is going to be lambda over 2, which is 0.390 meters divided by 2, or 0.190 meters. All right, and then in B, now the temperature is -5 degrees, so we can use this formula. V equals 331 meters per second. The temperature in degrees Celsius over 273 plus 1. So this is 331 meters per second times the root of -5 over 273 plus 1, which gives 328 meters per second. So the speed is lower on that cool day, or whenever the temperature is lower. And in this case, the wavelength is the same. So lambda is constant. So we have F equals V over lambda, 328 meters per second over 0.390 meters, which is 841 hertz. Oh, I'll just move that up. Example 6, water is pumped into a tall vertical cylinder at a volume flow rate R. The radius of the cylinder is lowercase r. At the open top of the cylinder, a tuning fork is vibrating at a frequency f. How much time elapses between successive resonances? The speed of sound in air is v. Okay, so I've drawn this rough sketch here. We have water coming in at volume flow rate r, which then changes the volume of the air column by the same rate, since the water level rises at rate r. And that's the volume flow rate, so let's start with that. We'll have r equals delta v over delta t, where v is volume. And then I can put the volume of this air column here, so pi r squared L over delta t. And I'm going to pull out pi r squared since it's constant, and we have delta L over delta t. Now this air column portion is closed at the water level here and open at the other end, so it's open closed. And we'll use that because we want to solve for delta t. So if I rearrange, I have delta t equals pi r squared delta L over r. And we want to plug in for that delta L. So since this is open closed, I have F equals NV over 4L. L equals NV over 4F. So if I want delta L, that's going to be delta N V over 4F. We're using a tuning fork, so it has a constant frequency. This is open closed again, so N is 1, 3, 5, and all odd integers. So the difference between any two successive resonant frequencies is 2. So this is 2V over 4F, or V over 2F. And now that we have delta L, I can plug it back in here to find an expression for the time. So I will have delta T equals pi r squared. Instead of delta L here, I'm going to write V over 2F. So V over 2RF. And that's what we wanted to come up with for an expression for the time that elapses between any two successive resonances.